Hi, this is Dr. Lewis. Just going through a typical problem that you might have got in workshops and could come up in the exam. And this is really about the basic idea of conjugation and showing resonance using curly arrows. So it says predict with reasoning, and that doesn't mean writing an essay, that means drawing a molecule and showing the curly arrows and the resonance forms you can get. For those which are conjugated, draw one other resonance form and the curly arrows that transform the given structure into the resonance form. So if there isn't resonance, then you do have to say something in order to explain it. So you can't just say not conjugated. So the first one is, as you can see, there are three similar ones. It's the allyl system, the 3-carbon system, which has conjugation. One's a radical, one's an anion, one's a carbocation. So we'll draw the first one. It's got a CH3 and an H, and there's a radical, and ET stands for ethyl. So the conjugated system is just that 3 carbons there. So remember, if you've got a radical, start with your one barbed arrow, and everything else must be one barbed arrows too. So that essentially means that one electron, that one paired electron, has gone in to form a new bond, and it must have another electron if it wants to form a covalent bond. So it takes one of those pi electrons from the adjacent bond, and then the other one goes on the end carbon. So there we have our new resonance form, and now the double bond is moved to there, and so nothing can change in the molecule in terms of its atomic structure, just the movement of pi electrons. And so now the unpaired electron is at the far end, so it's delocalized, but you only get unpaired electrons at either end, not in the middle. So the next one, the same structure, exactly the same structure, but now we've got an anion. Sorry, that's ET, isn't it? And so when it's a carbanion, that essentially means it's a lone pair. But organic chemists often don't, for carbon systems, write an anion and assume that everyone knows it's a lone pair. So we still draw curly arrows from the anion, even though strictly you should really start with a lone pair. And the only time that can get you into trouble is when there isn't a lone pair there. So some systems, such as, say, if I drew boron with 4 bonds to it, that's formally negative, but it doesn't have a lone pair of electrons. So you couldn't draw a curly arrow from the boron minus, because it wouldn't be a pair of electrons. So you just have to be careful that we know what we're doing. So I'm going to just draw the curly arrow starting, move it into the bond next door, and then that's generated another bond to that carbon, so we must move a pair of electrons away, otherwise we've got 5 bonds around the carbon. So we draw our resonance form arrow, and then we draw the same structure. ET, 2 H's, and now, so the negative, that lone pair has moved in, or negative charge, moved in to form the new pi bond, and the pi bond that was adjacent is now moved on to the end carbon, and that's where your negative charge is now. Right, so below, so that's the radical, the anion, and now the cation. So we've now got a carbocation, so 2 electron system this time. Same area is still conjugated. So remember, when you're doing resonance forms with curly arrows, the start of the curly arrow is always a pair of electrons. So you're not going to start at an empty orbital with no p electrons in it, if you like. So you're going to start from here, and you're just going to shift it into that bond there. That's going to generate, and that's only one arrow. So when you've got a carbocation in our system, you just essentially got one arrow, unless there are more it's an extended chain. So now we've got a pi bond there, and if you like, the electrons are going from left to right, so they're going to leave behind a positive charge, or you could say it's got 3 bonds to it, so that's going to be the positive charge. So that's the 3 allyl systems, and then we've got a cyclic system drawn like this. So that is an H there, so I'll just draw that, just one H in there. So the conjugated system is those 1, 2, 3, 4, 5 carbons there. So we could draw curly arrows, and remember, it must stop at that carbon because it cannot go into the bond. That's going to generate 5 bonded pentavalent carbon here, so that would be wrong. So if those 2 methyls weren't there, it would be more tempting to push that curly arrow into there. So that's why I say, if in doubt, always draw the hydrogens in all the carbons, and then you should know not to draw a curly arrow onto a carbon that's going to give you 5 bonds. So it stops on that carbon. There we go, and that would be all you need to do to show conjugation. However, as we've got a bit more time, you can show it going all the way back round to the other side, and remember, it stops on that carbon too. So now the anion stops there. That double bond is moved into there, and that negative charge from the previous one went into there. And finally, the last one is that one there. And we can see it's not a case of, it's not got double, single, double, it's double sp3. So there's an H there, all important H there. So that's sp3, not conjugated. Double bonds separated by insulating sp3 carbon. So that's just a quick way of saying it. So in the top system, we definitely had conjugation. And there we also had conjugation. There we had conjugation. And there we had conjugation. So, demonstrate conjugation with curly arrows. Make sure you don't go on to put curly arrows onto a carbon where you end up with pentavalent carbons. If you're worried about what you're doing, say for this sort of system, put the hydrogens in, say on the carbons, so you know where not to go. Okay?